All right, welcome to this explainer. Today, we're taking a microscopic, incredibly high-yield journey into what is easily one of the most misunderstood and absolutely vital molecules in the entire human body. We're talking about fats, or lipids. Now, if you're studying clinical medicine, biochemistry, or prepping for some massive medical exams, you already know lipids are a huge, high-stakes topic. They aren't just, inert tissue sitting there. They are dynamic, life-sustaining, and honestly, sometimes life-threatening. So we really got to shatter some preconceived notions right out of the gate here. Fats are not just energy stores. They're hormones, they're membranes, they're signaling molecules. From cholesterol acting as the precursor to vital hormones, to the very membranes wrapping every single cell in your body, lipids are literally everywhere in clinical medicine. And once you realize they're actually complex signaling molecules, their clinical relevance completely changes. Okay, let's just dive right into this. Here's our roadmap for today. We're going to decode fats and acids, map out digestion and lipid highways, dive into metabolism and ketones, look at the clinical stakes, and then wrap it all up with a high-yield rapid revision to lock it in. Let's start with part one, decoding fats and acids, the building blocks. Because before we can even touch complex diseases, we have to understand the basic nature of the lipid molecule. The absolute foundational concept you need to grasp is that a lipid is a hydrophobic molecule. Hydrophobic literally translates to water-fearing, which means they are completely insoluble in water. And since the human body is mostly water, this one chemical property dictates exactly how lipids have to be digested, packaged, and transported. I mean, they can't just float around freely in our bloodstream, right? They need highly specialized handling. So this fundamental water-fearing property drives how we classify them into three main groups. We've got simple lipids like waxes and triglycerides, and hey, pay close attention to triglycerides. That's a major exam pearl for energy storage. Then we have complex lipids, which make up our cell membranes. And finally, derived lipids, like cholesterol, a massive player in both health and disease, along with our fat-soluble vitamins. Now, drilling down specifically into fatty acids, there is a very high-yield structural distinction you gotta know. Saturated fatty acids have zero double bonds in their chemical structure. They are completely saturated with hydrogen. Unsaturated fatty acids, on the other hand, contain one or more double bonds. And while that structure difference might sound kind of minor, it completely changes how these fats behave, both in the body and in our diet. Within this world of fatty acids, some are deemed essential. Basically, our bodies can't make them from scratch, so we absolutely have to get them from our diet. I want you to lock this memory trick in right now. Lile. That stands for linoleic acid and alpha-linoleic acid. Seriously, whenever you see a question pop up about essential fatty acids, just think Lile. Moving right along to section 2, digestion and lipid highways, transporting energy. We know what fats are, so let's track the amazing journey of how they're broken down and moved around after we eat. Because fats hate water, digesting them is this tightly choreographed routine. First, bile salts come in, acting kind of like dish soap to emulsify these giant fat droplets. Once they're broken apart, pancreatic lipase steps in, chopping those big triglycerides into monoglycerides and free fatty acids. These pieces then bundle together into temporary transport vessels. Well, actually, think of them more like ferries, called micelles. They ferry the fats over to the intestinal wall to be absorbed. But once they're inside, they need a totally new vehicle to survive the watery bloodstream, and that first ride is handled by a structure called a chylomicron. And this brings us right to our highway metaphor. Think of lipoproteins as a fleet of delivery trucks navigating the bloodstream, hauling that hydrophobic fat. Chylomicrons are your first responders. They're transporting the dietary triglycerides you literally just ate. VLD trucks, they carry endogenous triglycerides, meaning the fats your body manufactured itself. Then there's the infamous LDL, delivering cholesterol. You probably know this clinically as the bad cholesterol. And finally, HDL. This is your cleanup crew, doing reverse transport, dragging cholesterol back to the liver. That's why it's earned its reputation as the good cholesterol. All right, part 3, metabolism, energy, and ketones, the mitochondrial furnace. We've digested the fat, we've shipped it, but how do we actually burn it? Ask yourself this right now. How do fats actually become energy? I mean, we always talk about burning fat, but biochemically, what does that even mean? The answer is found in a supercritical pathway called beta oxidation. The mechanics here are so cool. Beta oxidation strictly takes place inside the mitochondria, the powerhouse of the cell. In there, fatty acids are chopped up and turned into acetyl-CoA to make energy. But here's the catch. fatty acids can't just casually stroll into the mitochondria. They need a VIP pass. That's the carnitine shuttle. No carnitine, no fat burning, period. Now, contrast that directly with fatty acid synthesis, making fats. That happens outside in the cytoplasm, and it uses a totally different toolkit, specifically the enzyme acetyl-CoA carboxylase and energy molecules like NADPH. But what happens when the body is totally overwhelmed, or say, starving? It switches gears and makes ketone bodies, molecules like acetoacetate, beta-hydroxybutyrate, and acetone. These are produced exclusively by the liver. This system kicks in during prolonged starvation or uncontrolled diabetes mellitus, where the body is screaming for energy but can't properly use glucose. The absolute crucial clinical link here is ketoacidosis, a potentially fatal condition where your blood becomes dangerously acidic because of a massive buildup of these exact ketones. Which brings us nicely to Section 4, Clinical Stakes and Lipid Disorders. We've seen the elegant biochemistry, but what happens when the system completely crashes? All these disease states tie straight back to the mechanisms we just went over. Elevated LDL, that bad delivery truck, is directly linked to atherosclerosis, which is the hardening of your arteries. If triglycerides build up where they shouldn't, boom, fatty liver disease. A broader lipid imbalance, that leads to obesity. Remember our Lila essential fatty acids from earlier? If you're deficient in those, it shows up clinically as dermatitis. And if that essential carnitine shuttle or the beta oxidation enzymes like MCAD happen to be deficient, your body literally cannot burn fat for energy, triggering massive metabolic crises. Okay, Section 5, High-Yield Rapid Revision. Let's do a fast, last-minute review of the core concepts. So here is the absolute crucial bottom line. Triglycerides, that's your energy storage. Chylomicrons, dietary fat transport. LDL is the bad cholesterol, and HDL is your good cleanup crew. Beta oxidation happens inside the mitochondria, and it absolutely demands that carnitine shuttle. Finally, ketone bodies are the liver's SOS signal during fasting or diabetes. Master these one-liners, and lipid biochemistry becomes incredibly intuitive. So I'll leave you with this. With this biochemical blueprint in your head, how would you approach treating a deadly lipid imbalance? Because if you understand the enzymes, the pathways, and the transport trucks, you literally hold the keys to the clinical solutions. Keep exploring, keep connecting those dots, and thanks so much for joining me for this explainer.